cushion header. But Gerard! What a headshot!
I think it's about time for me to quit being a Man U fan. They're keeping on losing each week. Not good, Bangla, not good. Talking about losing, I think we're going to continue our video on losses inside pipe later. Okay, so stay tuned. Bye-bye. Boo. Hello, mate. I'm Darcy.
We're taking over the ship.
Just kidding. Okay, so today we're going to learn about the losses inside the pipe, and together with us we have about a few connectors together with me, and this is a way for me to try and help you understand the difference between major and minor losses. Okay, so the idea of losses inside the pipe, we will have two different types of losses inside the pipe, which is called as major losses and minor losses. For the major losses, it is highly affected by the length of the pipe. Okay, the length of the pipe. It means the longer the pipe, the higher the major losses, and it is affected by the friction inside the pipe. If you see it from here, this looks like the inside of the pipe is really smooth, but however, we have to know that each material will have some friction inside it, whether it is small or it is big. It depends on the material that we are using. Okay. However, for minor losses, it is affected by the connectors that we are using inside the pipe. For example, I have a T shape over here. So if I connect over here, and then we have a 90-degree bend over here. So these two connectors will provide some minor losses inside the study. Okay. To further calculate what will be the number for the major and minor losses, we will continue with a different video later. Okay, so stay tuned.
Welcome back everyone. So right now we are going to teach you on the calculations of losses in piping system. In a pipe system, there are losses between the pipe, and we have two types of losses. And the first one is called as major losses. Major losses is caused by friction in a long pipe. Imagine having a pipe system and having a fluid coming on one end of the pipe. So what will happen over here is the fluid will be in contact with the surface of the pipe, and this will create a condition where we have a no-slip boundary condition. And what does it mean by no-slip boundary is this surface will have an effect of friction towards the fluid. So because of that, what will happen is the flow will become much slower if the friction is much higher. So what will give the effect on the friction? So the friction is dependent on the type of material that we use for the pipe. So in this case, the longer the pipe, will equal to higher number of major losses. Okay, so we are going to go for the second one. Okay, for the second type of losses, it is called as minor losses. And minor losses is due to the piping system passes that we use throughout the piping system. So the passes that I'm saying about is actually various fittings, valves, bands. For example, you have a 90-degree band and the flow is going this way, okay? Or sometimes you have a T-shape where two flows comes into one outlet. And sometimes you'll have exits, which is when you have a reservoir and water is flowing out to the pipe. Or you have expansion, which is from a smaller pipe to a bigger pipe. Or you have a contraction, which is from a bigger pipe to a smaller pipe. So these different piping system passes will affect on the minor losses inside a piping system. Okay, so the friction caused the pressure drop in the fluid flow. So talking about pressure drop, what does it mean by a pressure drop? Okay, so imagine you have a reservoir at the top of the hill and you have a tank at the bottom of the hill. Okay, assuming this is a tank, we have opening over here. So the fluid inside is water, and we provide a piping system for the water to flow from one point to the other. Okay, so for us to understand the pressure of the system, we have to know what will be the pressure at the surface of the fluid. If you are talking about the surface of the fluid will have a condition where pressure, gauge pressure, will equal to 0. The same thing also will happen here. This is based on our study in chapter 2. Whenever you have pressure at the surface of a fluid and the fluid is meeting the atmosphere, the P gauge will be equal to 0. So if I assume this point to be 1 and this point to be 2, P1 and P2 will equal to 0. Okay, however, if I want to know what is the pressure at the top, for example, pressure of the fluid here and the pressure at the fluid here, you have to calculate the height distance between these two, and this is called as elevation difference. Okay, so if this is the height bottom and this is height of the top, and the elevation difference is called Z, or denoted by Z, and this one can be Z2 and this one can be Z1. So the difference between these two, Z1 and Z2, will be delta Z. Okay, or sometimes we call it as H. Okay, so if you remember from chapter 2, P gauge will be equal to rho, G and H. For this study, P gauge 1 is equal to rho 1 G1 H1, and P gauge 2 is equal to rho 2 G2 H2. However, because we are using the same fluid, assuming this part is water, and then the same water goes down to the pipe, for the tank, it is called as water also over here. So what we'll have is the density for 1 and 2 will be the same. So if we go for density 1 and density 2, it will be the same, so we can cancel out. And the gravitational force as we live in this world will stay the same to be 9.81 meter per second square. So G1 is also the same as G2. So in order for us to know what is the pressure difference between point 1 to point 2, will just be the equal of H1 minus H2. Okay, in piping system, sometimes we don't use the simple equation over there to find the pressure difference, because the system is involving a lot of losses in the study. So the calculation that we learned before is a condition where we don't have any friction at all inside the pipe. So to continue to find what is the losses inside a pipe, we have to know the equation for the losses. So we call it as delta PL, or this is called as pressure drop. Or pressure loss for all type of fully developed internal flows, which is laminar or turbulent flows, circular and non-circular pipe, smooth or rough surfaces, horizontal or inclined pipe. So this is universal for every different kind of internal flows. So delta PL, the amount of losses in pressure in the pipe, is equal to F L over D rho V square average over 2. Okay, F is called as Darcy friction factor, and this is highly connected to the type of material and from different material you will have different roughness, and I will show you how we will find the roughness for each material and how the roughness affects the F in our calculation later. So second one, L is the length of the pipe, D is the diameter of the pipe, okay, and then you have density, which is the fluid density, rho, and then you have V, which is going to be the velocity of fluid inside the pipe. In this study, L, D, density, and V square can be easily found using the condition inside the pipe. However, for F, we need a special study to get the number for F, and this relates to our calculations of Reynolds number. Okay, so to identify what is the F, we have to remember from Reynolds number, the video before this, whenever the Reynolds number is higher than 2300 or the same as 2300, we will have a turbulent condition, and whenever we have Reynolds number to be lower than 2300, we will have a condition called as laminar. So how does the turbulent and laminar affects the F? Okay, for friction factor F, if the condition is laminar, the friction factor is equal to 64 divided by the Reynolds number. And for condition where F is turbulent, we cannot use the same equation 64 over RE. However, we have to use two different kind of calculation method. One is called as Colebrook equation, and the other one is through a chart called as Moody Chart. And this one is an equation. Okay, when are you going to use Moody Chart and where are we going to use Colebrook equation? Actually, doesn't matter because both of them will give you the F that you want. But in our daily life, using Colebrook equation will take a longer time because the equation for Colebrook is one over F and then equals to negative 2.0 log epsilon over D over 3.7 plus 2.51 over RE F. And if you check from the equation, to tell the truth, even I don't remember this equation all the time. And what you have to do right now is you have to solve for this 2F over here in order for you to know what is the friction factor. Hard, isn't it? So that's why instead of using Colebrook equation, we will show you to use something that is much more easier, which is called as Moody Chart. Okay, so in order for us to see that, we have to check on the Moody Chart. Now, this is an example of a Moody Chart, and the Moody Chart consists of three different elements. The first one is called as Darcy friction factor. This is the one we are searching for at the end. Second one is the Reynolds number on the bottom axis, RE. And the third one is the roughness, epsilon over D. So this is epsilon over D, and it is called as relative roughness. In order for us to find friction factor through Moody Chart, we have to use the Reynolds number from our calculation to make sure that the flow is turbulent. Or if the flow is not turbulent or laminar, we can still use the Moody Chart because we have a line for laminar flow over here. However, usually for laminar flow, as I said before, we only use 64 over RE. So for Reynolds number, which is turbulent, we have to use the study of Moody Chart. So how do we use the Moody Chart? Okay, to use a Moody Chart, we have to actually provide you with a condition. For example, if our RE is equal to 50,000, which is going to be turbulent, far beyond 2,300, and if the pipe we are using is cast iron with a diameter of 0.1 meter, for example. Okay, if you have a condition like this, what we have to do is we have to know which axis that is important for the study. So in order to find F on the left side, we need to use RE on the bottom and also epsilon over D on the right side. Okay, so how are we going to go with this? Okay, first let me prepare you for the Moody Chart. First, we need to know what will be the best RE to be used in the Moody Chart. Okay, so if you have an RE of 50,000, we cannot use this number inside a Moody Chart because if you see from here, the Moody Chart uses one significant figure multiplied by a power of 10 to the power of 5, for example. So to prep our Reynolds number for the Moody Chart, we have to change it in terms of the Moody Chart's number. So what we have to do is 1, 2, 3, 4. So the RE will be equal to 5 times 10 to the power of 4. Okay, so if we go to the Moody chart, we will see that 5 times 10 to the power of 4 is, this is 2 to the 10 power of 4, 3, 4, and this is 5. So this is the point that we are going to use. Sorry. So the point we are going to use is here. So later we'll use a ruler to line up from number 5 times 10 to the power of 4. Please make sure that you are checking on the right power, because this is 10 to the power of 4 and 10 to the power of 5. So the 5 over here is equal to 5 times 10 to the power of 4, not 5 times 10 to the power of 5. This is the usual problem for the students when they are doing this calculation. Okay. Next, we have to know what is the epsilon over d for this study. So the relative roughness is based on two parameters, which is number 1, the epsilon, which is the surface roughness of the study or the material of the pipe. So how do we get the surface roughness? As I said just now, if the surface roughness is dependent on the material, okay, if the surface roughness dependent on the material, we have to check the material from the Moody chart. So check for the roughness in Moody chart. Where can we find the roughness? The roughness is actually here in this box over here. Okay, this is epsilon, and this is for feet, this is for millimeter. Okay, let me cancel out for you so that we can see it much better. So this is roughness, so in millimeter, so this is the epsilon. So if I'm saying that we are using a system where the material is cast iron, we can check from cast iron over here. The roughness will be 0.00085 feet and 0.26 millimeter. Since in our study we keep on using SI unit, so we just stick to the SI unit. We are going to use 0.26 as the number for the roughness. So based on cast iron, epsilon is equal to 0.26 millimeter. Okay, if you are using 0.26 millimeter, it is not the same standard way the calculation that we want to do with the diameter. So we have to make sure that the millimeter need to be changed to meter. So 0.26 millimeter is equal to 0.00026 meter, or 1, 2, 3, 4, 2.6 multiplied by 10 to the power of -4 meter. Okay, now we can do the calculation for epsilon over d. So epsilon over d is equal to 2.6 multiplied by 10 to the power of -4 divided by the diameter of 0.1 meter. And we can cancel off meter over here, so the epsilon over d will just be a ratio, and it is equal to 0.0026. Okay, so now we already have the preparation for our Moody chart calculation, so we are going to use this number in the Moody chart. Okay, since our Moody chart at the top is full of wordings and everything, so we are going to use a new Moody chart at the bottom. So now the RE is equal to 5 times 10 to the power of 4, and then the epsilon over D is equal to, sorry, I forgot just now, 0.0026. okay, 0.0026. Okay, how are we going to use the Moody chart? Okay, first what you have to do is you need a ruler for this. Okay, so find where is 5 times 10 to the power of 4. I need to show you it is actually here, so I said this now. Okay, 5 times 10 to the power of 4, and find where is epsilon b 0.026. 0.0026 will be in between 0.004, so somewhere in between here is 0.003. okay, and maybe somewhat here will be 0.0026, so at this point is 0.0026. okay, so what you have to do, bring up your ruler, put it on top of your Moody chart, and then for the Reynolds number, just draw a straight line from the number to the top. Okay, pardon my straight line, I have a ruler but it looks crooked also, but should be okay I guess. Sorry. And for the Reynolds number, we are okay, just draw a straight line. So this is the first thing to do, draw a straight line. And secondly, from epsilon over D, we have 0.0026 over here. Okay, now this is going to be incredibly hard, but we are going to try. We have to draw a line from this part up until we meet up with the part or the line from the Reynolds number. So we need to intercept the Reynolds number, so we have to draw a line, try to follow the curve. If the curve is going up, then you should go up also. Not the best, but it looks quite okay. So we meet up over here, so this is the point where we have interception. So this is the second part. Okay, for the last part, what you have to do, bring out a ruler again, and then you have to draw a straight line from here to here. Sorry, it's not working out. Once again, so wow, getting worse and worse, but I think you get the idea, right? So this is number 3. So if you check from here, this is 0.025, 0.003, so somewhere in between you'll be 0.026, 0.027, 0.028, 0.029, and 0.03. So in this line over here, if you draw it nicely, it should be in between 0.027 and 0.028. So in between that, you will have 0.0275. So we try our best to make it as clear as we can. Make sure when you are doing your study in Moody Chart, you use ruler, and make sure you use the right pencils and everything to make sure that we have a very smooth line, so we will get the right F. So assuming my lines are okay, so this is the F for the study. Okay, so the friction factor. So now the friction factor is equal to 0.0275. So how are we going to use the friction factor? So remember the equation from the top. Okay. And then the equation will be delta PL is equal to friction factor multiplied by L over D rho D square average over 2. Okay, and this is where we put the F that we have in our study. Okay. Besides using delta PL, we can also use H, or they call it as heat, in our study of piping, because in our common world of engineering, we rarely use delta PL in terms for our piping. We usually use heat loss, and heat loss is equal to HL, and it is actually coming from delta PL also, because delta PL will be equal to rho GH. Okay, since if you have water flowing from the top to the bottom, we are only going to use H at the end. So what will happen over here is we just divide delta PL with the rho G, which is the density and gravitational acceleration. So you will get this as your heat loss. So HL, or heat loss, is equal to delta PL over rho G. So HL is equal to FL over D rho V square average over 2 divided by rho G. So this will be cancelled out. So HL is equal to FL over D V square average over 2G. So we have two different equations in our study, and these two different equations can be used inside our piping system. So for HL major losses, we already discovered that major losses is HL major, and for major losses we will use this equation over here fully. So HL major will be equal to FL over D V average square over 2G. What about minor losses? Okay, so for minor losses, we don't have to use any friction factor, and minor losses we have to use something called as KL, and KL is equal to the loss coefficient. Okay, so before I go further into this, let me identify what is minor losses. Okay, minor losses is equal to HL minor, and it is equal to KL, or the summation of KL times V average square over 2G. Okay, imagine if you have a piping system. For example, I just cut off a piping system. You have a 90-degree bend, another 90-degree bend, and then you have a valve, for example. Okay, and then you have an expansion. Okay, and then you have contraction, and then you have a 90-degree bend, and then you meet another valve, a different type of valve. Maybe this is closed valve, this is check valve. Okay, and then the pipe goes the other point. Okay, so the KL for different type of passes will be different. Okay, for example, based on the definition that we have, the KL itself, for example, this is the 90-degree bend. Okay, this is also a 90-degree bend, and this is also a 90-degree bend. Okay, so it means over here we have 3 90-degree bends, and each bend will have the same KL, or we call it as KL 90-degree bend. Okay, for example, we have here a globe valve, and the globe valve will have their own KL globe valve, and this one, for example, check valve. For check valve, we have our own KL for check valve. Okay, so if you have expansion or contraction, we also have different KL for each one. Expansion, contraction. Okay, so how do we use all this KL inside our study? Simple. If you want to put in the KL inside the study, for example, for this picture, we can put HL minor equals to the summation of all KL. For example, we have 3 times KL for 90-degree bend plus KL for globe valve plus KL for check valve plus KL expansion plus KL contraction, and then multiply by V average square over 2G. So that will be your HL minor. Simple, isn't it? But you have to make sure that you take account every single valve, every single bend, contraction, entrance, exit, all the passes that you have inside the piping system. And each different bends or globe valve or passes will be having a different KL. Some might be the same, but a lot of them will be different from each other. So at the end, you know what is major losses and minor losses. So what can we do at the end? So at the end, we have to know what is the total losses of the study. So total losses inside the pipe will be equal to HL major plus HL minor. Okay, so it is equal to FL over D V square average over 2G plus the summation of KL V square average over 2G. So this will be your HL total, and this is a very important equation for you to remember. It's about 35 minutes of lecture right now, so I think I'll stop here and we'll meet you in a different lecture later. Till then, I'm Sham. Bye bye.
Okay, so through the calculations, now you know how the connectors over here and the length of the pipe is affecting the pipe network and the pressure difference between the pipe network. Okay, so this is the reason why if you are an engineer designing a piping system, you have to actually optimize the length of the pipe and to minimize the use of connectors to make sure that we do not lose any pressure in between due to these losses. Okay, so we are done for this chapter or subchapter. So we'll continue on the use of the study or the calculations of major and minor losses for the piping network. So till then, meet you on a different video. Bye bye. Hopefully many wins this